Yeah, hello class. Okay, so we're going to do our first lecture on thermodynamics. So today we're going to talk about heat and temperature. Now, these words are very familiar just from everyday use, but we have to be a little precise in what we mean by these things when we're in a science class. So to define them both, let's say we have two objects, which I'm going to call A and B. And say these objects are in what we call thermal contact with each other. So they don't have to actually be touching each other. Let me give you an example. Say A is a heater. So imagine you have a coil that you run a current through it and it's glowing hot. And B could be your hand. Obviously, if you touch the coil, you're going to get burned. But even if you just put your hand near the coil, you'll feel the heat from it. And so you're in thermal contact with it, even though there's no actual physical contact. Okay, so there's two objects, A and B, are in thermal contact with each other. And in some cases, energy is going to flow from one object to the other. So let's say it's going to go this way. So energy is going to flow from object A to object B. Now again, energy can flow for a lot of different reasons. There could be chemical reactions, mechanical work being done. But this exchange I'm talking about is kind of like just a spontaneous process that happens when these two objects are in thermal contact with each other. And we call this exchange of energy heat. So heat is just a form of energy, and it is measured in joules. That's our basic SI unit. So, it is energy, so nothing new there. But just when it flows spontaneously from one object to another, they're in thermal contact with each other, we call that heat. And joule is the SI unit that we're familiar with. There's another very common unit used called a calorie. Now, calories, they're not SI units, but they're very often used. And there's a conversion factor between them. Where 4.186 joules is equal to 1 calorie. Now, everyone, of course, is familiar with this word calorie. You see it on food labels all the time. And from what I know about biology, which isn't all that much, when your body breaks down carbohydrates, the chemical reactions are the end result, it's basically just like burning food. And so, that's why we use calories as a measure of like how much food you're going to get, or how much energy you'll get out of the food. And if you remember a joule, think of a mechanical example of a joule. That'd be like applying a force of 1 Newton through a distance of 1 meter. It's not that big of a unit. So this idea that a calorie is only around 4 joules, that might seem a little strange. Like if you eat food that has like 500 calories, you're not going to get too much out of that. And so this is how a calorie is actually defined. However, food labels, what you see in a food label, they're called calories. They're actually kilocalories. So if your food has, say, 100, if it's labeled as 100 calories, that would be, 100 kilocalories. And then you can convert that to joules. So that'd be what, 400 some thousand joules. That's a much bigger number. Now, calories are used, I don't use them very often, but you might come across those. Okay, so we have the spontaneous flow of energy. Now, why does energy flow from object A to object B? And for now, what I'm going to do is I'm going to say that object A is hotter than object B, or at a temperature the temperature of object A is higher than the temperature of object B. So this is our first use of the word temperature in this class. Now, that doesn't really necessarily answer why energy is going to flow from A to B in the first place, but ultimately, the subject we're talking about is thermodynamics. This was developed in the 1800s, long before, well, several decades before the atomic theory of matter was really accepted and understood. And so they didn't really have this modern understanding when this came about. Nowadays, we know that these objects, let's just say that these are two objects that are in actual physical contact with each other. So they're touching. And we know these objects are made out of atoms or molecules, usually molecules. If you have like a block of iron, that could just be atoms though. And they're moving around. The atoms are not perfect, or molecules, they're not perfectly at rest inside this object. And the hotter the object, the higher the temperature, the more energetic the motion of the molecules are. Now, if we're talking about solids, the solids don't really move. They have a particular location in the solid, but they vibrate around that location. In a liquid, they can actually flow around each other, so you can't say like one molecule is going to exist in one place and stay there, but they will in a solid. But in fluids like liquids or gases, they can move around even more. But even in a solid, they're just oscillating back and forth. And the higher the temperature, the more energetic these oscillations are, the faster they can oscillate. And so if you put these objects in contact with each other, there's going to be collisions between these molecules, and like substance A and substance B. And, you might remember from mechanics is there can be energy transferred in collisions. Momentum is conserved. Momentum is always conserved in collisions, but energy can be gained or lost. But it can also be exchanged between particles. But usually the faster moving particles lose energy, and the slower moving particles gain energy. So when you put these objects together, there's collisions at the boundary between them, and the molecules in substance A are losing energy overall, and in B, they're gaining energy. And again, this is occurring at the boundary, but you can think of it as like layers. So there's like another layer next to the boundary, and so if the boundary molecules of substance B gain energy, they're going to be moving faster, and they're going to be colliding with the next row of molecules over, and so this energy is going to flow throughout solid B. So overall, we just say from A to B. So we kind of define heat as that spontaneous flow of energy from one object to another. Now, when it comes to temperature, right now what we've established is the idea of kind of hot and cold. Nothing precise right now. But we can say like this object is at a higher temperature than, like object A is at a higher temperature than object B. We want to do better than that though. And again, if we had more objects, we could have, say, an object C and put that in contact with A and then put it in contact with object B and kind of see what direction energy is flowing there. And overall, we can kind of order things from hot to cold. Okay, but we want to do better than that. We want to have what we call a temperature scale. So we want a way to give a number to a temperature. So we can say this object is at a temperature and actually have a numerical value. So what we need for a temperature scale, we need two reference points. So we're going to start out with the first actual temperature scale that was devised. This is the Fahrenheit scale. So basically, we need two reference points, which are usually pretty arbitrary. And then we can divide it up and assign numbers to these two. We can kind of arbitrarily assign numbers to these two reference points. Now, these reference points could be anything, but it should be something, creatable. So you can say, well, let's just talk about the Fahrenheit scale. Maybe not the best example because Fahrenheit, he was the first one to build an actual working thermometer, which was a very big deal at the time. But he could actually build multiple thermometers and have them agree with each other. So that was actually a pretty important advancement. And he used body temperature as one of his reference points. Now, it's not a very good example because people have different body temperatures. And even an individual can vary throughout the course of the day. And, but again, that wasn't really too much of an issue in his time. They couldn't measure things that precisely. Just getting thermometers to even come close to each other, that was a pretty big deal by itself. And so, even if your temperature's off by a few degrees, maybe not that big of a deal. So that was one of his reference points. And the other was a mixture of salt water and ammonia. Okay. So we have salt, water, and ammonia. And you think this is as a reference point because this is the coldest thing you could come up with. So apparently, he might have thought that there's nothing colder than this, but obviously that turned out not to be true. Okay, so again, it's kind of arbitrary though, so nothing wrong with these. And he assigned them values 0 and 100. Maybe he had a temperature that day because now they say standard body temperature is 98.6 degrees. Which is probably, not a very accurate statement because that's 3 significant figures. There's more uncertainty than that. But, roughly reasonable numbers here. So let's say we have these two, these two reference levels, 0 and 100. And you could build a thermometer based on this temperature scale. So if you remember old-fashioned thermometers, actually some of you might not even know how they looked, but you had this glass or plastic container, kind of like a thin tube, and then there's a reservoir, and the whole thing was filled with mercury. Well, not completely filled. And the way a thermometer works, say we have, again, two objects, A and B. And let's say the temperature of A is greater than the temperature of B. So we know heat is going to flow from A to B. Now what happens when, so object A is losing energy because heat is just a form of energy. And when it loses energy, A is going to cool down. And B is gaining energy, and so B is going to warm up. And so eventually these two temperatures are going to get closer and closer together. Eventually they're going to be the same temperature. Energy is going to continue to flow as long as there's that temperature difference. So if you wait long enough, they will be in thermal equilibrium where they're at the same temperature. And so we can use that to design a thermometer. So let's say we take this saltwater ammonia mixture and we put our thermometer in contact, we put it in the mixture. And another thing we're going to talk about later, something called linear expansion, but you might be aware of the fact anyways, that typically when you heat things, they expand, and when you cool them, they contract. And so if we put this thermometer in this saltwater mixture, should have added ice to the mix. Now you want ice to make it cold. So you put it in this mixture, and the mercury inside the thermometer is going to get cold, and it's going to lose volume. It's going to shrink. And so this level is going to go down. And whatever level it settles at, once it's in thermal equilibrium with this mixture, it's at 0 degrees by definition, so we can mark our line right there. And then, again, take your temperature. You can put yourself in thermal equilibrium with this thermometer, and that'll cause it to heat up. So the mercury is going to heat up, and it's going to expand, and this mercury level is going to rise. And then when you're in equilibrium, you kind of mark off what that level is, and that's 100. And now, what if you place your thermometer in contact with something else entirely? Well, the water or the mercury level is going to settle somewhere. And so what we can do is we have these two levels, 0 and 100, and what we can do is just break it up into pieces. Like we can have 10 equally spaced pieces. Okay, I'm not actually drawing 10, but let's just say we had 10. I didn't really draw them equally spaced. But actually, that's not too bad. Okay. So yeah, like each of these tick marks would be 10 degrees. So this would be, like 50 degrees here. This is 60. So this might be like 58 degrees. You can make these tick marks smaller and smaller. And to make finer and finer divisions, you can read things more accurately. So that's the basic idea behind how a thermometer works. And once we have this thermometer, then we can measure the temperature of whatever we want. Now, I have to say whatever we want within reason, because this is just one type of thermometer. Something based on thermal expansion. So when you heat things, they expand. When you cool things, they contract. But that has its limits. One reason mercury is used for thermometers, or it used to be used, turns out mercury is pretty toxic, so they don't use it anymore in thermometers. I don't even think you can really find these. I found one of these at Walgreens and tested it out, and it said I had a temperature of like 107 degrees or something. I decided just not to trust that thermometer, and just didn't worry about it. So yeah, I don't know if there's any accurate thermometers based on thermal expansion anymore. Mercury thermometers work great. Now they're all electronic, and I'm not sure if I trust those too much either, but okay. So there's limits with that kind of thermometer that's based on thermal expansion, because when you cool things down, like say we built a thermometer out of just normal water, that would obviously have its limits, because if you cool this down, what's going to happen to the water? Eventually it's going to freeze, and then this won't work anymore. It would actually fail before you got to the freezing point. Water is unusual in that sense, that if you have, say, water at like room temperature, and you cool it, it is going to contract like everything else does. But then when you get close to the freezing point, it actually starts to expand. which is an unusual property of water. So it would fail before it even froze. And again, another limit, if you heat things up too much, what do? They'll evaporate. And it's like every material has its kind of limitations for use as a thermometer. Mercury is really good because it has a, something we'll talk about more, like how much energy does it take to actually heat up mercury or water? And it turns out water takes an enormous amount of energy to cause it to heat up, to change the temperature of the water. You need a lot of energy. Mercury, much easier to heat and cool. So you don't need an extreme temperature change to cause it to rise and fall. So, or you don't have to wait as long at least. So mercury is a very good substance to use. But again, and it also has a very low, freezing point. So it's a very good thing to use. It's just that it's toxic, so we don't use it for that anymore. Now, there are other ways of measuring temperature. Lots of other ways. Probably the most precise way, the most accurate way to measure things is with something called a thermocouple. You have different metals at different temperatures. And yeah, we're not going to really get into that, but they can be used to measure things very accurately. That's one thing you want in any measuring device. You need to know how accurate it is. But also like a range, like what kind of temperature scales can we use? Thermometers are great for things around room temperature, or you have cooking thermometers that can go up to hundreds of degrees. But measuring extremely low temperatures, something like this old-fashioned thermometer just isn't going to work. But, this is the only one we're going to really talk about. Actually, I do want to talk about one more type of thermometer later, but at least we have an idea, and this allows us to actually assign numbers to temperatures. So now we can have a temperature as a number, which is great. Now, unfortunately, the Fahrenheit scale, this is the first one that was designed, and I actually like the Fahrenheit scale because it's, got a pretty good range. Most things we interact with are between 0 and 100 degrees. So it's actually a really nice scale. Unfortunately, it's not the SI scale. So the SI scale, we use Celsius degrees, which, again, you're probably familiar with because pretty much the rest of the world measures things in Celsius. Okay, now Celsius has 2 reference points as well. And one thing that's nice about Celsius, it has somewhat logical reference points. Let's just use water. And we can look at the boiling and the freezing points of water. And so let's arbitrarily assign these values 0 and 100. Now again, I'm saying let's use water. Again, we have to be a little bit careful because water itself isn't a perfectly well-defined thing. You think water, H2O, well that'd be pure water, but if you turn on your sink, what's coming out is not just pure hydrogen and oxygen in water form. There's minerals in it, and unfortunately there might be some pollution in there, but so normal water isn't necessarily pure. And also another factor is pressure. And again, you might be aware of this. Like we say boiling water. We say water boils at 100 degrees Celsius. Again, that's not necessarily a true statement. And if you've ever gone to Colorado, that's the highest point in the continental United States at least. Actually, I think the highest point is in California, Mount Whitney, but a lot of people live at high altitude in Colorado, and if you want to cook food with, like, say you're making spaghetti or something, it just takes longer if you're at a high altitude. And that's because the boiling point of a substance like water depends on the pressure. And at a lower pressure, it boils easier at a lower temperature. And so you can heat water up till it's boiling. And this 0 and 100, these are at like standard atmospheric conditions. So these are just at like standard atmospheric pressure. Just kind of a tricky thing to define because pressure depends on altitude, which is why if you go to Colorado, it's at a higher altitude, it's a lower atmospheric pressure. But again, it depends on other things as well, like the weather. You know, pressure drops before a storm comes in, things like that. So you can't even define it as a location. There's a lot of factors. But pressure, actually, we can define it precisely in something called pascals. So a pascal is a Newton per meter squared. Like a pressure is a force divided by an area. So we do have like a standard pressure, we can just give it a value. Might as well tell you what that is. Let's say P0 for like standard atmospheric pressure. It's around 1.01 times 10 to the 5th newtons per meter squared. So that would be the standard value. It's kind of like an average typical value you'd get around sea level. So again, you have to be precise. If you're going to make a thermometer, you want to make sure you have pure water and under the right pressure. And again, we can define a thermometer just like we did before. We just have different reference levels. Okay, now this is what we mostly use in science, is the SI system. Actually, this is not the SI unit for temperature. We're going to get to that later. But this is kind of related to it. This was the next major temperature scale devised by Celsius. That was his name. Okay, so we have two temperature scales. And yeah, they're both in use. And I'm actually glad. I wish we switched to metric a long time ago. We almost did once, I think in like the early 90s or something. They came real close to switching. I think Congress voted, they were like one vote short of actually pulling that off. But I am glad for the Fahrenheit scale. I actually prefer that one. But most of the world uses Celsius, so we need to know how to convert from one scale to the other. And there's kind of two approaches that we can have to convert one to the other. So I think it's best to look, well, first we're going to talk about this graphical method. Okay, so we have a graphical, more like a picture method, not so much a graph. Let's say we have, I'll draw it first. Yeah, let's say this is boiling and this is freezing. And say this is the Celsius scale and this is the Fahrenheit scale. And so we know the values here. I mentioned on the Fahrenheit, let's start with Celsius. We know water freezes at 0 and it boils at 100. So we know those values. Now, unfortunately, Fahrenheit was based on a different reference levels entirely. They used some salt, ice water, ammonia mixture that was much colder than normal freezing water. And so the actual reference level for, on the Fahrenheit scale, would be somewhere under down here. But in the Fahrenheit scale, they kind of redefined it so that water freezes at 32 degrees and boils at 212. Okay, so we've got these two temperature scales. And we kind of redefined the reference level. So now everything is based on boiling and freezing water under standard conditions. And Now we just have these kind of strange values here. It might seem a little weird. Why would we make 32 and 212? You know, maybe like 0 and 200 are better or something, but there's historical reasons why these have these unusual values. They're based on different reference points entirely. So I think the best way to go about this is let's look at an example. Let's say we have a temperature of 60 degrees Fahrenheit, or let's say Celsius. 60 degrees Celsius. What is that? That's going to equal something on the Fahrenheit scale. We want to find what that is. Okay, so we're going to look at this graphically. Now, 60 on the Celsius scale is going to be right around here. You know, it's 60% of the way from 0 to 100. Now, first, before we do anything, let's look at this here. If you go from freezing to boiling on the Celsius scale, we're looking at 100 degrees. So I'm going to write down 100 degrees Celsius. What's the change going from those same two, freezing to boiling on the Fahrenheit scale? You go from 32 to 212, that's 180 degrees. And we're talking about, the same change going from freezing to boiling. So on one scale, it's 100 degrees. On the Celsius scale, that change would be 100 degrees. On the Fahrenheit scale, that'd be 180 degrees. So we can write down this equation. However, there's a major problem with this equation. And that is we can use temperature in two different senses. Very often, when we talk about temperature, typically, like what's temperature outside, you just want a number, like it's 25 degrees. But in this context, we're talking about changes. And because of this offset, depending on how you interpret this equation, it might make sense or it might not. So what I mean by that, the way I described it, this equation makes perfect sense. Because we're talking about a change on the Celsius scale and comparing it to a change on the Fahrenheit scale. However, if you just look at this equation, you might think 100 degrees Celsius is equal to 180 degrees Fahrenheit. But that's clearly not the case. 100 degrees Celsius is 212 degrees Fahrenheit. And so this equation only makes sense if we're talking about changes. And it can be confusing. So what we do is they invented this kind of other notation that we can use. So there's two ways we can, use the word temperature. One would be just like a measurement, like it's 20 degrees outside. And so we could say it's 20 degrees Fahrenheit. So what they decided, if we're talking about changes in temperatures, instead of saying degrees Fahrenheit, we'll say Fahrenheit degrees. And we also write it differently. So we can say T equals 20 degrees Fahrenheit. That's a temperature reading. If we're talking about a change in temperature, let's say delta T, I'll use a different number. Let's say 10 Fahrenheit degrees, we'd write it this way. So if we're talking about readings, it's degrees Fahrenheit. If we're talking about changes, it's Fahrenheit degrees. I think if you look at older books, you see things like this, and you just have to understand that we're talking about changes. But I like this idea of rewording it and having separate notation. And so now, without any confusion arising, we can say 100 Celsius degrees is 180 Fahrenheit degrees. So just the notation itself implies that we're talking about changes. And because they have common factors, let's divide everything by 20. And I'm going to write this conversion factor down here. I'll kind of leave it up here for a while. So we have 5 Celsius degrees is equal to 9 Fahrenheit degrees. So that's a conversion factor. Now, one thing in this class, well, it's an online class, so that's a little different, but even like back before the pandemic, when we were actually in class, you'll have an equation sheet that you can use for tests. So, yeah, that'll be online, and you don't need to memorize things like this. So that will always be given to you. This kind of numerical data, things, and even equations, you don't really need to memorize things like that. Okay, so we have this conversion factor when we're talking about changes on these scales. So, again, this was 100 here, like this change on this scale was 180, and so we get this conversion factor. So now if we just look at this here from 0 to 60, obviously that's a change of 60 Celsius degrees. So how much of a change is that on the Fahrenheit side? Well, let's use our conversion factor. 9 Fahrenheit degrees is 5 Celsius degrees. These cancel out. 60 divided by 5 is 12. 12 times 9 is 108. So the change is 108 on the Fahrenheit scale. Okay, now the question is, what is this temperature though? And again, we're talking about changes here. So it's like if we start at 0 and go up to the temperature of this object, we've changed 60 on the Celsius scale. We know we've changed 108 on the Fahrenheit scale. But again, look at the picture. On the Fahrenheit scale, we started at 32. So the actual temperature here would be, 32 plus 108, which is 140 on the Fahrenheit scale. Okay, so that's just one example of changing from like a Celsius to Fahrenheit. Let's do one going the other way as well. I'll just make up a number. Let's say it's 20 degrees. That might actually be accurate. Right now, because it's December. Oh, well, you'll be seeing this in January, but right now it's December. And so, say it's 20 degrees. So we're somewhere over here. We're beneath the freezing point of water. And so we're at 20 degrees. And so again, let's use this as our reference. Let's go down here. If we start at the freezing point, we're going down 12. So we have minus 12 on the Fahrenheit scale. And now if we use our conversion factor, we have 5 Celsius degrees over 9 Fahrenheit degrees. So let's see, 12 times 5 is 60, divided by 9. What's that? Oh wait, why? Is that right? Okay. Let's just say 6.7 on the Celsius scale. Okay. And again, that is a change. So as we look at the picture, we're starting from the freezing point, which is 0. So again, now going down to this level, we're going 0, and we're changing in the negative direction by 6.7. So we just go to minus 6.7 degrees. Okay, So this is one way we can convert between these two temperature scales, and I really like this method of doing it. Now there are other ways. We're going to talk about one more way using an equation. Nowadays, a third way you could do it is just ask the internet. Go on your phone or Google, whatever, and it can do all these conversions for you, but it's important to know how to do it yourself. And the reason I like this way is you can just see that things make sense here. 20 degrees, we know we have to get a negative number. And again, you can kind of look at this scale, like based on if you draw it accurately, like say you did a problem and you had, say, let's go back, say we had 60 degrees Celsius, and let's say somehow we ended up with like 90 degrees on the Fahrenheit scale. So let's say we said 60 degrees Fahrenheit, or I'm sorry, 60 degrees Celsius. Say we did that and found 90 degrees Fahrenheit. If you look on this scale, 90 degrees Fahrenheit, going from here to here, that's 180 degrees. So we should be, maybe, like if we go in the middle, that would be 100 and something. So yeah, we can just tell they don't line up. And so, and particularly, or if we got like say 300, we're on the wrong side of this boiling point, or if we got a negative number. But you can kind of see visually if your answer makes sense or not. So yeah, this is obviously wrong, and yeah, graphically, you get this perspective that you don't always get with equations. So I like doing it this way. We're going to talk about this equation method as well. So I'm going to, let's go over that. And this is convenient because it's very practical. So again, let's start with a problem. Let's say we have 45 degrees Celsius equals something in degrees Fahrenheit. Okay, so our goal is to come up with an equation, and we're going to plug in our temperature in Celsius, and the answer our equation is going to give us is a temperature in Fahrenheit. So let's say TF is a temperature in Fahrenheit. So we're going to have TF equals something, where we're going to plug in our temperature on the Celsius scale and do something and get the temperature in the Fahrenheit scale. Now the thing about this, the conversion, is that it has to be a linear equation. Just the way we define these temperature scales, they are linear. We break it up into equal intervals. So there's going to be this direct relation between them, a nice linear relation. So we can write it like this. So TF is ATC plus B. Where we plug in, say we knew what A and B were, then we plug in like 45 degrees Celsius, multiply it by A, add B, and that'll give us our answer. So that's the idea. Now the goal is to find A and B. Now how do we do that? Well, there's some things that we know. Let's say we plug in, I'm going to write this over here. What we know is so again, we have a function of the temperature on the Celsius scale. We have a function of Tc. So let's say Tc is 0. 0 degrees on the Celsius scale, that's 32 on the Fahrenheit scale. So if we plug in, if Tc is 0, Tf has to be 32. The other thing we know, I should put this picture back up that I erased. I'm going to erase it again. I think we'll need the room. But here's what we had. We had Celsius and Fahrenheit. So we had 0, 100, 32, and 212. So yeah, if we plug in TC as 0, that'd be this number. We have to get TF as 32. Similarly, if we plug in 100, we have to get 212 out of it. So we have two things that we know. We can write down two equations now. And we have two unknowns, and that's a very good sign when the number of equations is equal to the number of unknowns. So let's do this. And it turns out this is going to be very simple, because if we plug TC in as 0, TF is going to be 32. So we know 32 is going to be A times 0 plus B. So we already know what B is. So B has to be 32. So let's look at the other thing we know. If we plug in 100, we get 212. So 212 is going to be A times 100 plus B, which is 32. Let's plug that in there. So now all we have to do is solve for A. So if we subtract 32 from both sides, we have 100A equals 180. 212 minus 32 is 180. If we divide by 100, let's divide by 20. That'll even be a little more familiar. That means A, yeah, I'll just do it like that. So on this side we have 5A equals 9, or A is 9 over 5. And again, that fraction might look familiar, pretty much right there. Those numbers 9 and 5. Okay, so now we can fill in these values. Different ways we can write this. We can write it as a fraction. You're going to write this over here. A equals 9/5, and B is 32. If we want to, we could write B as 160 over 5. If you multiply 32 by 5, you get 160. And so now we can write our equation kind of in two different ways. TF is 9 over 5 times TC plus 32, or we can write it in this form. We can say 9TC plus 160, whole thing over 5. So whichever way you like to do it. Okay, so again, this converts from Celsius to Fahrenheit. So let's actually do this. For this number, works out very conveniently. Let's just use this first equation. So here we have 9 over 5 times 45 degrees Celsius plus 32. And yeah, it's convenient because 45 over 5 is 9. 9 times 9 is 81. So what do we get? 113. So if we have 45 degrees Celsius, that should be 113 Fahrenheit. And yeah, if we just look at, like, say, right in the middle, here. Let's say that's 50 degrees. If we add 90 to this, because remember, if we look at just in the middle of these two values, that was 180 degrees. So the middle would be adding 90 degrees. That'd be 122. So again, 45 would just be a little bit under here. And 113 is a little under 122. Yeah, so it's good to check graphically just to make sure that this worked out. Now, this is going from Celsius to Fahrenheit. If you want the other equation, you can just solve for TC equals something times TF. So you can use the same equation to go either way. So we're not going to bother with the other one. Okay. Now, I mentioned that Celsius is not actually the scale that we use. That's not the SI unit for temperature. So what I want to do is talk about another kind of temperature, another kind of thermometer entirely. I'll leave that for now, I guess. So I'm going to draw something, and again, if you were going to actually do this, we're going to describe an experiment that could be done. And the experiment would be a little different than what I'm going to do. We're just really focusing on the concept here. So I'm going to simplify it a little bit. Okay, so what we have is this container on the left that's filled with some kind of gas. And on the right, we have this, let's just say there's air in this container right now. And we have mercury in this tube. And this is a hose. We have two tubes connected by a hose. So mercury can flow freely between them. And so, again, if we just have air everywhere, you know, the mercury level is going to be the same. Okay, now what if we heat up the gas over here? So there's a gas, like could just be air in this tube. Now it's a little unfortunate in our physics sequence, the 121, 122 sequence. Chapter 11 in the book is on things like pressure. Well, more generally it's on fluids. Covers things like pressure, which we skip here. And this is something that I do want to actually talk about, though, a little bit. Pressure is defined as force over area. So pressure is equal to force over area. And the units are newtons per meter squared. We give that a name, Pascal. He was a mathematician and a scientist. You might have heard of him in an algebra class, like binomial coefficients, Pascal's triangle. Yeah, he was generally, mathematician, physicist. Okay, and so 1 Pascal is 1 Newton per meter squared. Now, atmospheric pressure, standard atmospheric pressure, I'm going to call that P naught. It's around 1.01 times 10 to the 5th power pascals, or newtons per meter squared. So what I want to do is, let's look at this board here and try and estimate pressure, the pressure on the board, because we're surrounded by air, and fluids like gases and liquids, they exert pressure on the walls of their containers in all directions. They push outwards. And so there's air in this room pushing on the board. How much force is that air exerting on the board? Well, let's take a look at that. We have to estimate that. I should have brought a meter stick. But let's just rough estimate the area of the board. Let's say it's 1.4 meters. It's probably a meter tall, just to make things... Again, we don't really care about the exact numbers much. I want to get an idea how much force the air is exerting on this board. So let's just say the area of this board is 1.4 square meters. Now the force is the pressure times the area. So we have 1.01 times 10 to the 5th newtons per meter squared times 1.4 meters squared, or around 1.4 times 10 to the 5th power newtons. Now, if we kind of convert this to kilograms, even though they're not the same thing, but just like under normal gravity, again, if we're just doing an estimate here, like an equivalent weight would be a mass of around 1.4 times 10 to the 4th power kilograms. That's a very large mass. So basically, there's what I'm claiming is that the force that the air is exerting on this board is about the same as, say you had the board horizontally and you put this mass on top of it. That's about the same amount of force, which is kind of a remarkable statement to make. You know, is it true? Do you even believe that? And, well, yeah, it is true. Let's get away from, this would be like 14,000 kilograms. Maybe a more. So again, a car might be like 1,000 kilograms. So it'd be like, imagine this board horizontally, and you stack up like 14 cars on it. Actually, like very large cars. What I'm claiming is that that force is being exerted on this board right now by the air in this room. This is an amazing thing. Which again, you might be questioning, how is that possible? Or what if I had this board, like I could hold it like this and lift it up without any trouble? Am I that strong? Well, no. So what is actually going on here? How is it possible that there's that much force exerted on this board? And the answer is, there's air on the other side of the board pushing just as hard. And so we're surrounded by this fluid that's actually exerting enormous forces on us, but we don't really notice it. It doesn't have much of an effect most of the time. Now, if you're driving, that definitely has an effect. Air resistance. You have to push the air away. You know, so you have to exert a force on the air. Air exerts a force back on you. But so yeah, drag forces like air resistance are very noticeable. But just this overall, this pressure is surprisingly large numbers that we're just, you know, mostly not even aware. We don't even feel ourselves. It doesn't seem like we have the air pushing on us. But, yeah. And again, that's why if you go like underwater where the pressure is a lot higher, if you're like swimming deep underwater, you'd feel that, like in your ears. If you go deep enough, you'd feel it on your lungs because your lungs are filled with air pushing out. But if there's more force pushing inwards, it can become hard to breathe. Your lungs can't expand. So, yeah, they're surprisingly large numbers, but they mostly cancel out. But anyways, yeah, it's just because we skipped that chapter. Now, the pressure of a gas. So again, we've got this gas pushing down and on this mercury. And so that would cause this end to lift up. Let's say there's a fluid in here. Or maybe even we have a vacuum in here. Yeah, let's say this is a vacuum. Probably better if it was. So let's make this a vacuum. And so if there's a gas pushing down, that's going to lift this level of mercury upwards. And the more you push down, the higher this mercury is going to go. And so what we have here, we actually have a device where we could, the hotter this is, the higher the mercury goes. So this is a thermometer. We can use this device to measure temperature. And also by the height of this, let's say this is a reference level, the height of this column of mercury will give us the pressure of this gas as well. You might even see if you watch a Weather Channel, atmospheric pressure, I erased it, but that was around 1.01 times 10 to the 5th pascals. I think that's 760 millimeters of mercury. It's another way they measure pressure. You might see that on the Weather Channel. And again, that's because we use mercury. So that's how much this column of mercury would rise. And again, it's going to rise for any column of mercury, regardless of how, the cylinder containing it. You might think if there's a bigger cylinder, it's like a wider cylinder, there's more mercury, there's going to be more weight pushing down, so it's going to be harder to lift. But if it's a wider cylinder, remember, force is pressure times area. So there's going to be more force pushing up. So again, you can show it doesn't matter what size, what the diameter of the cylinder is. It's always going to rise to that same level. So I think this number is 760. 780 is a possibility. I don't use it very often, is why I don't remember it. I think it's 760 is standard atmospheric pressure. That's another way you can measure pressure. So what we have here is we have a device that can simultaneously measure temperature and pressure. And specifically, we're measuring the pressure of this gas. So what I'm going to do is make a plot. All right, so yeah, let's say we have pressure here. You can say pascals, doesn't matter. Say we have temperature on Celsius scale here. And again, we have a way of simultaneous. So if we do this experiment, we'll get a data point. We'll get a particular temperature and pressure. And we can repeat this experiment under different conditions and get a plot of how the pressure is going to depend on the temperature. And our data points might look something like this. As you lower the temperature, the pressure decreases. So let's say we get some data points. And again, we've got to stop eventually, because we have a gas. Erase the picture, but our thermometer involved a gas. So maybe we can draw this here again. Smaller version. So yeah, there's a gas in this container. And then that's hooked up by a tube or by a hose to another container. Oh yeah, there's some mercury in this one. And there's also mercury in this one. Okay. And so again, we'll have this like some reference level. Again, this will measure the temperature and pressure. But again, we're measuring the temperature and pressure of this particular gas. Now, we're going to talk more about this later, but there's different states of matter, like solid, liquid, and gas. And when you cool a gas, eventually it's going to turn into a liquid. Typically, hotter things tend to be in a gaseous state. Like on a scale, I guess the coldest things would be solids, and then liquids, and then gases. Of course, different materials, like mercury, for example, is a metal, but at room temperature, it's a liquid. So like different elements will melt or freeze at different temperatures. But when things are very cold, they tend to go into the solid state. And then if you heat them up, like take ice. Ice is cold. If you heat it up, it's going to melt and turn into a liquid. If you put that liquid in a pot and put it over a fire, eventually it's going to boil and evaporate, turn into a gas. And so here, we can cool this gas only so far. So let's just say say this was helium. And again, we can take a lot of different measurements. Like we could put this helium in contact with something cold, and we'll get this data point. And then we heat this up a little bit so we get a new temperature and pressure, and so on. And it seems to follow this line. And there's only so far our data can go, because eventually this thermometer is going to break down. We're going to the gas will turn into a liquid, and this will no longer work. Okay, and so, but if we take this line seriously, we follow this down, eventually there's going to be this point here where the pressure of the gas is 0. And then if we follow it to even lower temperatures, again, there's nothing wrong with going into negative temperatures. Just, we're taking this class in the winter, we might experience negative temperatures. But we will in the Celsius scale. So again, negative temperatures are fine, but eventually we'll get to negative pressure if we continue to follow this line. And that makes no sense at all. Gas is pushed outward on the walls of the containers, so the idea of a gas exerting a negative pressure, that's a little weird. But again, we don't have to even worry about it because this line, we're going beyond the data. So it's like we'll never actually get data where it goes into negative, so we could basically just ignore it. However, something interesting happens though if we change this to a different type of gas. Let's do that. Let's say we replace this with neon. That's another gas. Okay, we'll get data that's also going to follow a line. It'll be a different line. But if we plot this, we're going to find, like, for this, I'm not sure which of these lines should even be steeper. Let's just call this gas 1 and gas 2. If you go follow this line to where you get to 0 pressure, it's going to occur at the same point, the same temperature. And again, you can have a third gas, and you'll get another line. And they all kind of meet up at the same temperature. And so this seems to be a very special temperature. On the Celsius scale, this is around minus 273 degrees Celsius. I think it's 273.15. I usually just use 273 though. Good enough for us. And so that's a very special temperature. And so we say that we give this a name. We call this absolute zero. And the rule is, this kind of represents a lowest temperature you can have, although what I said was not accurate in any way. Technically, it's possible to have negative temperatures, but that's not something we're going to get into in this class. Kind of depends on what you even mean by temperature. We think of it in terms of like how energetic the molecules in the gas are, and in that sense, a negative temperature would never have any meaning. But there's other ways of defining temperature where you can actually have negative temperatures. But another thing I said is this kind of represents the lowest temperature you could have. We're going to learn later that you can never actually achieve absolute zero. So if you have something, you can cool it down, and you want to get to absolute zero, you're never going to make it. And the reason why kind of goes back to the basic idea that heat wants to go from hot to cold. So say we have this object, and say we make this cold. Okay, but heat wants to flow in. So I'd say this object is in some environment. The colder this is, the more heat that wants to go into it. We can isolate it, but heat spontaneously wants to flow into the material. And we're going to see later that you can take, in order to lower the temperature, we have to take heat out, which is kind of the opposite direction that it wants to go. Now, it can be done, but you have to do work in order to remove heat from this object. And the colder this is, the colder the object becomes, the more heat you'd have to remove to cool it down. So let's just say, for example, say we remove like 10,000 joules of energy from an object, we'll get a certain temperature change. The temperature will decrease a certain amount. Say we remove 10,000 joules of energy again, you get another decrease, but it'll be smaller because you're at a colder temperature. It's harder to remove that heat. And again, you keep removing that same fixed amount of heat, and the temperature drops every time, but the drop is going to get smaller and smaller. And it turns out to actually reach absolute zero, it's one of these limiting processes where it would require an infinite amount of energy to actually reach absolute zero. And again, we don't have an infinite amount of energy to use, so you can never cool something to absolute zero. You can get extremely close to it, but not actually there. Okay. So Kelvin scale, or sorry, absolute zero. Now, again, we have, I'm going to erase this picture. I'm going to write this down now. All right, absolute zero. It's around minus 273 degrees Celsius. Okay, so now I'm going to erase this. And let's look at the temperature scales that we have. We have Celsius and Fahrenheit. So again, this is the boiling point of water. This is the freezing point. And we have Celsius and Fahrenheit. Actually, I'm going to move these over. So again, Celsius was originally defined in terms of the freezing and boiling points of water. Fahrenheit was redefined, so they have this common reference levels. But again, remember these levels are arbitrary. You know, why water? Why not any other liquid? And so, but now we have this idea. We have a temperature that's not arbitrary. This is zero. We're never going to get. We're never going to reach that level. So again, we can keep on lowering the temperature lower and lower, but we're going to have like a floor here, where this is absolute zero. Now again, I mentioned negative temperatures are possible. Again, it depends on what you mean by temperature, but there's another definition where negative temperatures are possible, but again, not anything we're going to concern ourselves with at all in this class. And so we can look at this as an absolute limit. And again, the normal kind of things we're dealing with, we're never going to lower anything down. This represents the absolute limit. And so what we're going to do is, why don't we set this as one of our reference points? So why don't we invent a new temperature scale where we can say absolute zero is zero. That seems like a logical thing to do. And the scale is called the Kelvin scale. It's named after a guy who went by the title of Lord Kelvin. They don't give us titles like that anymore. They can call it Lord because you're smart. Yeah, those were the days. But yeah, they don't do that anymore. Yeah, Kelvin, he was around in the 1800s. One of the most prominent scientists at the time. And he did some really interesting theoretical arguments about temperature, and we'll talk about later. But they named this scale after him. And so again, we have an absolute zero as our zero. Now, what about the other reference point? Like, we also need like a size. Like here, to go from freezing to boiling, that was 100. And the Kelvin scale, we're just going to do that. So again, absolute zero is minus 273 on the Celsius scale. And so we're going to adopt the same, like a 1-to-1 conversion. So here we have 5 Celsius degrees is 9 Fahrenheit degree. I'm going to say 1 Celsius degree is 1 Kelvin. Now, one thing about the Kelvin temperature scale is you don't really say degrees Kelvin, you just say Kelvin. So like 40 Kelvin, you don't need to say degrees. Similarly, we're talking about changes. So here we're talking about a change of 40 Kelvin or change of 1 Kelvin. So again, there's this 1-to-1 correspondence. And so this is 0, this is 273, and this is 373. So basically all the Kelvin scale it's the exact same as the Celsius scale, except it's offset by this number, 273. So that will give us absolute 0. We could easily write down an equation. Oh, one more thing. Like here, for temperatures on the Fahrenheit scale, we say TF. On the Celsius scale, we say TC. For the Kelvin scale, we just say T. And so we can say T equals TC plus 273. So yeah, let's say TC is minus 273, then T would be 0, and that works out. Okay, so Kelvin, it's basically the Celsius scale, just offset. And this is the SI temperature. That's the unit for temperatures in the SI system. Now, normally you don't really have any, there's no reason you need to use SI units. You can use any units you want. However, we do want to be very careful. In this particular one, we're talking about temperatures. And usually when you see a temperature in an equation, it has to be an absolute temperature, like measured in Kelvin. Now there's another scale. It's basically, I think it's called the Rankle system, or I don't even remember the name. I've never seen it used, but I do know there exists. Like an absolute 0 based on Fahrenheit degrees. But no one uses that. But that would actually be a valid thing as well. And again, just to illustrate the reason for this, I'm going to write down an equation we're going to come across, and then until chapter 14. But I'm going to write down this equation. I'm sure many of you are familiar with this already. This is the ideal gas law, where this is pressure. This is the pressure of a gas. V would be the volume. N is the number of moles. And again, if you don't know what moles are, don't worry. R is the gas constant. And T is the absolute temperature. And again, this applies to gases. It's called the ideal gas law because if you have it kind of breaks down at some point. This basically is a gas where the particles don't really interact with, they don't get in each other's way. But if you have like an extremely dense gas, this equation would not be valid any longer. It would have to be modified. But basically, this is, under normal conditions, this equation is valid. Now the reason I say we have to be careful though, is, I said this is the absolute temperature. Because if you're working with Celsius, you could very well have a negative temperature. So let's say we want to solve for the pressure of a gas. We have nRT over V. Well, N is the number of moles. That's like a measure of how much gas there is. R is a constant. This is positive. Volumes, of course, are always positive. So if we plug in a negative temperature, we'll get a negative pressure, which, again, makes no sense at all. So again, or you could even have a temperature of 0 degrees Celsius, which would mean the pressure is 0 if you made that mistake of putting it in here. And so again, that just doesn't make sense. So whenever you have a temperature in an equation, you have to make sure it's based on this absolute 0 scale. Most of the other times you don't need to worry about using SI units, but T means absolute temperature. The only exception, I say usually, the only exception, if you see delta T in an equation, if you're talking about a change in temperature, you can use Celsius or Kelvin. It doesn't even matter which one you use. Okay, so like if you have a temperature change, say you have a gas that was at 325 degrees Celsius, and it cooled off to, say, 211 degrees Celsius. You might have, like, in your mind, okay, I remember temperatures, we have to be in Kelvin. Well, let's actually do this. Let's look at changes. Let's calculate. Here, I'm just going to erase this. Went from 325 to 211. So let's look at delta T on the Celsius scale. It's going to be negative. 325 minus 211, what's that? Minus 114 Celsius degrees. Okay, now I erased the equation. But basically T is Tc plus 273. So if we decided to be careful and convert these to Kelvin, let's add 273 to each of them. Maybe it'd even be more instructive if we just wrote it out. So if we convert to Kelvin, delta T would be our change. We take our final value. That'd be 211 plus 273. To get it to a Kelvin scale. And then we subtract our initial temperature would be 325 plus 273. And again, these are both in Kelvin. So, we converted them to Kelvin. But if we just distribute this minus sign, we can write it this way. 211 minus 325. So we're taking this minus that. And then we have the other terms. Here we have 273 and then minus 273. This one was in Kelvin. So again, here we have 273. Now we have minus 273. And again, these two just completely cancel each other out. So 211 minus 325, that'd be minus 114 Kelvin. So it's just an offset, and you're applying the same offset to both the initial and final values. So if you subtract them, it makes no difference if you do that or not. So as long as you're talking about temperature changes, you're perfectly fine sticking with Celsius. But if you have temperature readings, then you want to convert to Kelvin if you are going to use an equation like that. All right. I think that's actually it. Yeah. So that's it for this lecture on kind of the basics about heat and temperature.